Good morning. My name is Ritik Banerjee, and I'm going to talk about carbon nanotube based field effect transistors. I'm from the Department of Electrical Engineering at the State University of New York at Buffalo. So the flow of presentation would be such that first we will discuss about what exactly is CNT or carbon nanotubes, and then we will go on to why do you actually need CNFET or carbon nanotube based field effect transistors, and what are the advantages that you get over a MOSFET. And then we'll also discuss a CNT based FET fabrication technique. And at the end, we will also talk about one application of CNFET as compared to a regular MOSFET. And we'll also compare the performance and try to prove the fact that CNFETs are actually better, both in case of performance and in case of size modulation when it comes to practical application. So starting off with the basics, what exactly is a carbon nanotube? A carbon nanotube is nothing but an allotrope of carbon, and what allotrope is actually it's a kind of molecule, or it's kind of a compound which is made from the similar kind of molecules, but their properties are different. So, for example, if you have a diamond, if you have graphene, and if you have carbon nanotubes, so these are made from carbon molecules, carbon atoms, but these have very different properties when it comes to physical and chemical reactions. So basically talking about, we'll not go on to the fabrication of carbon nanotube, but what structurally carbon nanotube is. If you take a graphene sheet, now graphene sheet is formed when you have a long chain or long connections of hexagonal placed carbons having covalent bond between each other, and when you take that sheet and roll it over in a certain fashion, you end up with a tube. This tube is called a carbon nanotube. It has some interesting properties. The properties of these can be modulated by the amount of layers you put onto and the way or the fashion you twist it. Uh, Basically, what it's our interest in this field is its conductivity. It is highly tense. Its tensile strength is also high. Its flexibility is also high. But our interest here is the electrical conductivity. So talking about electrical conductivity, why do you think why does it have a high electrical conductivity? Is that because the electrons are actually in a covalent bond format, and which could travel over this mesh connection. If you can see, then if you can see it this picture, then these are the individual uh, at carbon atoms, and uh, the electrons are actually shared between these two, so it's very easy for an electron to travel in this zigzag or in this continuous path, which gives it some amazing electrical conductivity properties. It has high electrical conductivity and obviously low resistivity. So there are different types of carbon nanotube, and the basis of difference are actually two. One is the number of layers you have. You can have a single walled carbon nanotube, which is the area of interest at this point of time. You can also have multi-walled. Application of multi-walled is limited to two layers, because when you increase the layer of carbon nano or carbon graphene sheets, say you go to three layer or quadra layer, what happens is that intermolecular forces come into act, which actually hinder the structural integrity of the tube as well as the uh, properties of the tube as a whole. So till now, important usage has been limited to two layers. Now, the properties of this tube also depend on the fashion you twist it and on the type of rolling. You actually end up with two type of carbon nanotubes. One is the zigzag carbon nanotube, and one is the arm cell configuration. So, talking about the rolling, we have something called the graphene rolling. We take into consideration two indices, which is generally termed as N and M, where N and M are unit vectors along two directions in the honeycomb crystal lattice of the graphene sheet. if the value of m is 0, as in the vector rotation towards the direction of m is negligible or is 0, you end up with something called the zigzag fashion, which you can see here. It's this way. And if n equals to m, where there's an equal amount of rolling, then you end up with something called the armchair configuration. So you can see these tubes might look similar, but when you see on the orientation of the individual atoms, it's different from this and that. These two are pretty different when it comes to their electrical properties. Well, their physical properties are the same, but the electrical properties are different. Now, if you have the value where n equals to m, then what happens is the carbon nanotube you end up with is actually metallic in nature. But if you have a condition where n minus m is actually a multiple of 3, then the carbon nanotube you get is actually a semiconductor. And the most interesting part is if n minus m equals to 3, what happens is the band gap is pretty small. But otherwise, if all these two conditions are not true, if n is not equal to m and neither is n minus m equal to 3, then you actually get a carbon nanotube with moderate semiconductor properties. Our interest lies in the second half where n minus m equals to 3, or where either neither of them are true. If it is metallic, you actually use the nanotube to connect the drain and the source. So if you have a metallic strip which is connecting the drain and the source, you actually make a short circuit, and it'll never act as a switch. Well, the diameter of the carbon nanotube is governed by this formula, which is root over 3 a naught by pi into root over n square m square plus mn, where a is actually 0.142 nanometers. What is 0.142 nanometers? It is actually the distance between each individual carbon atom. So why do we actually need a carbon nanotube based FET? Uh, Metal oxide have been extensively used for storage purposes and as a switch also. Uh, but these have a limitations over size and over squeezing them on a chip. What happens is over the period of time we have got to know that when you reduce the channel length below 45 nanometers, the gate channel length, some quantum phenomena come into play which actually reduces the efficiency of the device. One which very important such phenomena which is actually overcome by CNFET is a short channel effect. To describe exactly what short channel effect is, let us consider the first one as a long channel and the second one is a short channel. These two might look similar, but let us say that this is actually 10 micrometers, the gate length, and this is actually 10 nanometers in length. What happens is when you start increasing the drain voltage, in both the cases from 10 millivolt to 1 volt, you can see there's a squeeze in the gate, but the gate is still present, the gate voltage is maintained. But in case of a short channel, the gate is almost absent. There's an abrupt drop, as you can see here. So now what happens is your transistor is no more controlled by your gate in this case. In this case, your gate is actually unexisting and it is directly a small gap between source and drain, and what happens is the source is actually connected to drain and it is again a short circuit. So you lose control over your device if such a condition arises, which arises when due to this short channel effect. Now, short channel effect has been distributed into five types, which is away or which is apart from the scope of today's discussion. But just for our knowledge, we'll know that there are certain types: drain-induced barrier lowering, which is what I explained. Then we have surface scattering, we have velocity saturation, impact ionization, hot electron effect. The above effect actually lead to a high power consumption and reduces the device's reliability, and at the end you actually lose control over your device. To the right, you will see two graphs. The first graph is a long channel, the second one is short channel. As you can see, in both different drain voltages, at VD is 1 volt and VD is 10 millivolt, the characteristic of ID versus VG, which is the output characteristic, is similar, just there's a shift. But in case of short channel, when you increase the gate voltage from 10 millivolts to 1 volt, you actually lose control over the properties of your transistor. The switch off and switch on stage is no more there. There is a loss in control over your transistor, which is a problem. So that's why we introduced something called the carbon nanotube based FET structure. Here you can see you are using a carbon nanotube, which is a semiconductor in this case, to connect the source and the drain. The gate sits over the carbon nanotube. Now, the effects of making such an alteration of introducing carbon nanotubes below the gate is that even in when what happens in case of MOSFET is when you decrease the gate oxide thickness or the gate thickness, there's something called quantum capacitance which comes into play and which increases with increasing gate voltage. But it has been observed in case of carbon nanotube based field effect transistors that with the increase of gate voltage from 0.5 volt and above, your quantum capacitance actually reduces. So if you can see here, this graph, then these are the gate thicknesses, which varies from 0.7 nanometers to 1.5 nanometer, which is actually very, very small. And you're increasing the gate voltage from 0.5 volt and up, you can see that your quantum capacitance is actually reducing to a significant level. So what happens if is that when you increase the quantum capacitance of the gate, it leads to something called the propagation delay, or which and it also leads to performance degradation. Propagation delay is the delay which the transistor takes for transiting from one state to the another. So which is a big problem. So as you can see that in with the introduction of carbon nanotubes, your quantum capacitance is reducing to a high level, which is again significantly important. Uh, Another important thing is the threshold voltage. So you never want the threshold voltage to be very low, because that is also a problem. Uh, there's something called a sub-threshold voltage. There's something called a threshold voltage. The threshold voltage is the voltage below which the transistor is considered to be off, and above which the transistor is considered to be on. So if your threshold voltage is very low, then again you tend to lose control over your device. In this case, what happens is, if you see, when you take the channel length below 20 nanometers, uh, the threshold voltage for MOSFET or regular MOSFET actually reduces significantly. This dip you can see, but it is an advantage in case of CNFET that it actually increases. It's not wise enough to say that this increase is something which we really want, but this is definitely what we don't want. So obviously it's better to have something which is okay than to have something which is completely not acceptable. So again, we can see below the range of 20 nanometers, you tend to lose control over your MOSFET. So again, a carbon nanotube, introduction of carbon nanotube helps you to keep control over your device. And we also have an added advantage is that these carbon nanotube based FETs have a threshold voltage which do not change with increase in room temperature or increase in temperature of the device or of the whole chip itself. You know, when you jam pack so many devices on a chip, you actually tend to increase or produce a lot of heat. So as you can see, the threshold voltage is a significant property of a transistor, and it does not really change with increase in temperature. Even on 10 times high temperature, it's not a huge difference, or not a huge difference. in the threshold voltage. So now we'll talk about the fabrication of CNFET. In this in these slides, I've tried to. There are many ways of, or many types of ways of fabricating carbon nanotube based FET. In this case, we have tried to duplicate the normal FET or MOSFET so that the structure made is comparable to the present technology of MOSFET, and their comparison can be done. So here you can see that here the gate actually sits over the carbon nanotube. You can have the gate below the carbon nanotube. The properties won't change much. Will actually not change at all. Uh, this is the final product that you want. The carbon nanotube based field effect transistor. This is actually a SEM image. SEM is a scan electron microscope to give you a clear idea of how you can actually uh, share a single gate. This strip is actually a single gate which is shared by two individual transistors. Again, this helps in integration and reducing size of the device. So here are this is the step of fabrication. So what you do is you take a silicon dioxide wafer, which can be either p-type or n-type depending on the electron concentration, and then what do you do it, you clean it. For cleaning you can use ultrasonic bath or you can expose it to UV according to your ease, uh, and then you use sputtering to deposit a 120 nanometer layer of SiO2 over the silicon crystal. And then you use a technique called dichlorine solution spinning, which is used to actually fabricate or uh, produce nanotubes over uh, uh, this wafer that you have, this SiO2 layer that you have. Then the source and the drain electrodes can be patterned using electron beam lithography, uh, and for that we use something called mask, which is actually a polymethyl methyl clarate. Uh, Once you are done with e-beam lithography with the presence of this mask, the polymer mask, you do something called a lift-off using titanium. Lift-off is when you actually etch away that mask to expose the surface, and you are left with two titanium strips which acts as your drain and your source. We make sure that the drain and the source have a separation of something around 200-300 nanometers, and this can be made sure by a SEM, a scan electron microscope. And once you're done with this, you need to anneal the whole sample at around 850 degrees centigrade for 10 seconds. Uh, Annealing is actually baking or heating of the sample without the presence of oxygen. Once you're done with that, you can actually using plasma enhanced chemical vapor deposition, or PECVD, you have to deposit a thin layer of SiH4 as a protective layer over the titanium aluminum titanium gate and drain, sorry, source and drain. And then uh, using annealing technique and in presence of nitrogen oxide, nitrogen dioxide, we have to pattern the gate over these two drain and source using electron beam lithography. So at the end, what you should get is something like D, this one, which is your transistor, and now you just need a contact probe or a two-point contact probe to draw three wires, one from the drain, one from the source, and one from the gate. Now, the particular fabrication technique led to the production of that CNFET, whose output characteristic is as shown here, which is similar to the output characteristics of present MOSFETs. And yeah, this is just to prove the fact that this product or this um, device that you made is actually acting like a MOSFET. Uh, and not anything else. Now, now you have the CNFET and you have the MOSFET, and you want to make a real life comparison that how is this better. You know that you can shrink it to smaller sizes, but is it better if if at all we at the end of time or in future we are able to reduce the size of MOSFET also to a scalable size of a carbon native FET? Is it going to be comparable? So in this case, we fabricated, or the author fabricated, a CNFET where the gate is 65 nanometer, and practically, in case of MOSFETs, the problem arises only when you start reducing the gate size below 45 nanometers. So this is a CNFET, and you have a MOSFET with comparable, which can be compared in real life situation. So two parameters were taken into consideration. One is the threshold voltage, again the voltage at which the transistor turns off and on, and one is the speed at what it does. So for the threshold voltage, they considered a simple inverter circuit to see how fast it inverts from 1 to 0, or how long it takes, or what is the amount of voltage it takes to convert from 1 to 0. Now, there's something called, as I mentioned earlier in my presentation, there's something called a sub-threshold voltage. So what actually happens is when you turn off a transistor, it actually does not really go back to zero at once. It gradually turns off. So what I mean to say is there's something called a sub-threshold voltage, which is present inside the transistor even after you have turned off the transistor. So what I mean is there is still a loss going on inside your transistor once it is switched off to. So it is computed, or the two devices, the MOSFET and the CNFET used, had a threshold voltage of 500 millivolt and 250 millivolt, and obviously the sub-threshold voltages will be less than that. So for our comparison, we have used a sub-threshold voltage for MOSFET to be around 250 millivolt, and for the CNFET to be around 150 millivolt. And as you can see by the results, that the lower part is actually the threshold voltage, and this is the threshold voltage, and this is the voltage applied. So what you can see is when you reduce the threshold voltage, uh, this takes a longer amount of energy is lost. The energy curve in this is much higher than the energy curve in this. What happens is you still have potential inside your gate till your voltage gate is still 500 millivolt, but here it goes, or it dies at 400 millivolt. So you're saving a lot of potential, you're saving a lot of energy. So power consumption is high in case of MOSFET, because your V output is not going to zero, whereas in this case it is a little bit lesser than that of a MOSFET. Now the switching time, here you can see for the switching circuit, for switching time we have considered a ring oscillator circuit, and there was a significant difference in the switching state time. Uh, the CNFET is actually 100 times faster than the MOSFET. The switching time is in CNFET is 2.42 terahertz, whereas in case of MOSFET it is 0.267 gigahertz. So it is significantly faster. So what you can conclude from this is not only CNFET helps you reduce the size of your device uh, without affecting or hampering your control over the device to a significant level over MOSFET. It also helps you uh, to give better output characteristics, better switching time, and better efficiency on the same size also. Plus, as you saw, the fabrication technique is not something very complex, and it can be done, and you can fabricate a CNFET pretty easily, keeping conditions under control, and keeping the environment clean. You can actually fabricate it in a fab lab. So all these things give rise to the fact that that CNFET is definitely something which is an area of interest and which definitely will become something more significant and more useful than a MOSFET in the coming days. Uh, Thank you. These are the references. These are the three papers that I have mainly used to refer for this purpose, for this presentation. Thank you.